Welcome to the AI Research Roundup. I'm Alex, and today we're looking at a paper from the Hugging Face trending list, published on July 27, 2025, so just about 3 days ago. This paper introduces a new preference optimization method that shows an impressive 12.32% absolute win rate gain on the Alpaca Eval 2.0 benchmark. The paper is titled MaPPO, Maximum a Posteriori Preference Optimization with Prior Knowledge, and as we'll see, this new approach manages to improve results without adding any extra complexity. It presents a framework that incorporates prior reward knowledge to enhance how we align LLMs with human preferences, moving beyond current techniques. Alright, so to really get why this new method is needed, the authors provide a great visual. On the left, we see what happens with a common approach called direct preference optimization, or DPO. It relies on maximum likelihood estimation, which can cause a problem called the squeezing effect. As the model trains, the likelihood for both the chosen and the rejected answers actually drops, just to create a bigger gap between them. Building on that, the chart on the right shows their new approach, Maximum a Posteriori Preference Optimization, or MaPPO. By incorporating prior knowledge, it mitigates this harmful tendency, leading to a more stable and effective alignment. This table really drives that point home, showing the log probabilities for different methods. Log probability is just a score for how likely an answer is, and less negative is better. With direct preference optimization, the score for the good answer drops from minus 14.3 to minus 121.5. But with MaPPO, it actually improves to minus 10.4, showing it avoids penalizing good responses. To see this in action, the authors show a concrete example. The prompt is a simple math word problem. We see two responses, a chosen one and a rejected one. But here's the key. Both of them are actually correct, arriving at the same answer of 12. Their reward scores are super close, 0.95 and 0.91. This is a classic near-tie case, where both answers are high quality. A method like direct preference optimization would still try to harshly penalize the rejected response, which is what maximum a posteriori preference optimization avoids. Building on that, this diagram shows how maximum a posteriori preference optimization works in a practical, iterative loop. It starts with a prompt which is fed into the current policy model. That's just the LLM being trained. The model generates a couple of responses. Then, a separate reward model, which is another AI that acts like a human judge, scores these responses to pick a winner and a loser. This new preference data is then used to tune the policy model further, making it better for the next round. This iterative cycle is key to its online learning capability. So, a key question is whether this is a standalone trick or a more general principle. This table shows it's the latter. The authors use maximum a posteriori preference optimization as a plugin, adding it to several existing alignment methods, which are all just different flavors of direct preference optimization. And the results are pretty striking. Across the board, on benchmarks like Alpaca Eval 2.0 and ArenaHard, adding their method brings consistent and sometimes huge improvements. For instance, on ArenaHard, the score for regular DPO jumps by over 13 points. And this main results table really lays out the evidence for that broader effectiveness. The authors test their method on a whole range of models, from different families like Quinn 2.5, Mistral, and Llama 3. They compare it against the baseline called instruction tuning, which is a standard fine-tuning approach, as well as both offline and iterative versions of direct preference optimization. The takeaway is clear. Adding maximum a posteriori preference optimization consistently boosts the scores, often significantly. For instance, with the Mistral 7B model, it adds a massive 12-point gain on the Alpaca Eval 2.0 benchmark. So to wrap things up, maximum a posteriori preference optimization offers a more principled way to align language models. By using prior knowledge, it avoids unfairly penalizing good answers, and it delivers consistent improvements across different models and existing methods, all without adding extra complexity. That's it for this episode of the AI Research Roundup. I'm Alex. Thanks for listening.